So what I'm going to show you is 3 characteristics of simple harmonic motion. The first and most important one you already know, and it's most important because it's the one you use to prove. So if someone says, or a question says, show that such and such is moving in simple harmonic motion, okay? This first characteristic, that's the one you're going to show. Much like, you know, if you had to show that a function's an even function, okay? What you have to prove is this. Okay, like that's the result, and once you've got that, you say, therefore, it's an even function, okay? So I'm going to show you that first one, which you already know, but then I'm going to look at the other 2, I'm going to show you how they work, not because you can quote them as actual results, but because you get asked to prove them so often, I might as well show you how it works, okay? So, number 1, and I said you already know this, it's the differential equation for acceleration. Hopefully if I say this enough times, it'll get, have it into your head. My sister's a dentist, and she says, if you want people to do things like floss or brush regularly or something like that, you have to say it 3 times. And then they actually remember it. First and second times, it just totally goes whoosh. So the differential equation for acceleration, I think I've said it like 10 times by now, but anyway. What is the differential equation for acceleration? This is acceleration. For simple harmonic motion, what's it equal to? You remember? Yeah, success. Okay. So all this means is, the further you get away from the origin, from your center of motion, from your equilibrium position, the further away you get, the more you get pushed in the opposite direction. Okay, that's what that minus is about. Okay. So if you ever get asked to prove that something is simple harmonic motion, this is where you have to go to. Okay. But this leads to a couple of other characteristics. Okay. So firstly, what kinds of functions obey this kind of property, show this kind of characteristic. And the kind of properties are, the kind of functions are wave functions. So anything which moves in simple harmonic motion should move according to a wave function. Now, do you remember this back from when we did auxiliary angle? Okay. The basic kinds of wave functions are x equals, now I'm going to give the standard form here, a sine mt plus alpha, or, so just your regular old sine function, or a cos function. Okay. Now let's have a look at both of these for a second. You'll often get asked to describe the simple harmonic motion of a particle. Okay, just like you've been asked to describe the motion of a particle, it slows down, it stops, that kind of thing. So what kinds of characteristics do we know about these? All the same characteristics you remember from like year 10 and graphing trig functions. Okay, so for instance, you're going to need to know the amplitude is A, right? Okay, so that's going to be a constant. You're going to need to know the period. How long does it take for this object to go through one cycle of simple harmonic motion? And if you've got an n here, right? I'll move it over here. This is a bit abstract, so let's just do a concrete example first. Sine x, right? Or sine, sorry, I'm doing t's, right? Thinking in radians, what's the period of sine t? Just regular old sine. 2 pi radians, right? So if I adjust it just a little, and make that 2t, how does that change the period? It halves it, right? So in other words, because it's 2t, I get 2 full cycles within that original 2 pi, right? So 2 cycles in 2 pi equals pi. So therefore, if I've got n out the front, what's my period going to be? The relationship between period and this coefficient is division, right? So here it was 2 pi on 2. So therefore here it'll be 2 pi on n. So they'll ask you for period of motion all the time, okay? And then this guy hanging off here is just the phase, right? But importantly, for the sine function, right, it's going to tell you where you begin. So you might not actually start at the origin. You're going to start at an offset, okay? Now, remember I told you we had this idea of wave functions. We introduced the name when we were doing auxiliary angle, right? Auxiliary angle. Now, when you look at these 2 equations, they're kind of already in auxiliary angle form. There's the auxiliary angle there, the phase, right? But what did the equations come from before we crammed them into one sine function or one cosine function? What did they start off as? Remember? we actually had to do all of this work. We said things like sine x plus cos x, right, is going to be root 2 sine, and then you've got whatever you want here, plus or minus alpha, right? Whatever it was, pi on 6 or pi on 3 or something like that. So therefore, this is what you're used to seeing, right? But one wave function is the same as two wave functions, or 3 or 4 or 5, right? So you might not get one nice neat one. You might get two separate ones, like this. Just be careful with my letters here. Yeah, okay, so I'm calling them B and C because they have to be different coefficients to this original A, right? And if I have two functions here, so long as they have the same period, right, I'm going to end up with another one of these wave functions, okay? So any of these, they all exhibit simple harmonic motion, all right? So